Welcome to another AP Chemistry video focusing on Unit 8. Today we are going to continue our work in acids and bases by breaking down weak acid and base equilibria, as well as some acid-base chemical reactions. Now, if you remember before, we talked about strong acids and bases and how they 100% completely dissociate, making it very easy to determine the hydronium and hydroxide ion concentration. Today, we're going to be looking at weak acids and bases which do not completely dissociate. This plays a couple little tricks that we have to work on and figure out in order to determine all of the different things such as hydronium and hydroxide ion concentration. Join me, won't you? By the end of this video, students will be able to determine concentration of solutions from weak acids and bases. They should also be able to explain the relationships between pKa and the value Ka. You should also be able to calculate percent ionization of an acid or base, as well as write out acid-base reactions and buffer reactions, which we'll talk more about in a later video when we go into detail on buffers and how they work. So remember when we talked about strong acids, we said that they 100% completely dissociate. So for example, if I had 0.1 molar HCl, that would result in 0.1 molar of my hydronium ion concentration. Weak acids and bases, however, only partially dissociate. Usually this is less than 10%, which means that most ions remain unionized. So this results in an equilibrium situation where we take our weak acid and we put it into water and we get some amount of products, but we retain most of our reactants. So because of this, we can actually write an equilibrium expression for this and get an equilibrium constant for K. Because this is an acid-base reaction, we refer to that as Ka. And remember that with our equilibrium expressions, it's always our concentration of our products divided by the concentration of our reactants. Remember that we do not include water because water does not have a concentration. So much like equilibrium, the magnitude of Ka predicts how much H plus is produced in a reaction and thus how strong the acid base is. This is also given to us by using pKa, very similar to how we looked at the negative log of H to determine the pH. We can take the negative log of K to get what's called pKa. The lower the pKa, the stronger the acid. So thinking about it in terms of equilibrium, larger Ka value indicates that the reaction equilibrium shifts more towards the products than the reactants. So if we have a very large Ka value or a low pKa value, that indicates a shift towards the products, indicating greater dissociation and more hydrogen ions, thus a stronger acid, if we think about our dissociation equation we looked at previously. So if we look at the pKa values in the table, we can determine that the lower the pKa, the stronger the acid, because we have perchloric, hydrochloric, sulfuric, and nitric at the very bottom, those of which you know are strong acids, meaning they result in nearly 100% dissociation. Whereas the ones at the top are not strong acids. So therefore they have a higher pKa and therefore are considered weaker because when they are placed in water, less of it dissociates into its hydronium ions and its conjugate base. The same concepts apply to weak bases as well. In terms of your dissociation equation, your base plus water gives you OH minus and your conjugate acid. Your Kb value, which should say Kb, not Ka, is listed there, and obviously the negative log of Kb is going to give you your pKb, and same thing, the lower the value for pKb, the stronger the base is. A couple other things to keep in mind in terms of conjugate acids and bases in terms of this is that the stronger the acid or the base, the weaker its conjugate is. So for example, HCl is a strong acid. Its conjugate base is extraordinarily weak. Same thing here, when we look at some of our strong bases that are towards the bottom, or stronger bases, the acid strength is relatively weak. So do kind of keep that in the back of your mind. And just a couple of net ionic equations when we react certain things together. So for example, if we react a strong acid and base together, leaving out our spectator ions, our net ionic equation is going to be H plus OH minus yields H2O. With weak acid and a strong base, remember that the strong base will completely dissociate. So whatever is attached to it at the front, whether it be Na, Ba, Ca, whatever, is a spectator ion. Ha, however, being a weak acid, does not completely dissociate, so we don't break it apart like we would normally in a net ionic equation. So therefore we get Ha just some acid plus OH minus gives us A minus with water. And base works kind of in a very similar way. We have our base, we have our strong acid, which completely dissociates. I just wrote it as H3O plus, and then we get our conjugate acid and water. So we also can consider Le Chatelier's principle when other compounds are added and how that might shift towards a higher or lower pH. So for example here, if I were to add something that has an, in the very first equation here, if I add something that has an anion that is A minus, remember that when we add more product in equilibrium, that shifts the reaction to the left. If we shift the reaction to the left, that produces more OH minus, therefore making the solution more basic. So those are just a couple of other things to keep in mind, that we can think about these things in terms of equilibrium, as well as Le Chatelier's principle when other compounds are added and how that shift might impact the pH of the solution. So in order to determine the pH of a weak acid or weak base or whatever, we need to know the H plus concentration. The problem is that unlike strong acids, weak acids don't completely dissociate. So we need to experimentally or mathematically determine how much we're going to get out of it. We can do that by setting up something that is called a Rice table. And I think we've talked about this previously in the equilibrium unit. Rice stands for reaction, initial, change, and equilibrium. So we write out the dissociation reaction above when we put it into water, and therefore we get H3O plus and an anion there. Now our initial is only going to include 0.15 molar acetic acid because that's the only thing that we have when we initially start the reaction. So we start off with 0.15 molar of our acid and then 0 concentration for my other materials. The change, however, is going to be a little bit different here. We don't know how much is going to dissociate, but we do know that however much we lose of CH3COOH, I'm going to gain in H3O plus and CH3COO. Basically what that's saying is that however much I lose of one of my reactants is going to become part of my product. So I lose X in my reactant part and I gain X and X in my products. For every X amount of CH3COOH that dissociates, I'm going to gain X as H3O plus and CH3COO. So when I combine these things together, what I get is 0.15 minus X and then X and X on the other side. Conveniently, I'm also given the Ka value for acetic acid. So what that means is that I can plug this into an equilibrium expression and essentially solve for X. So my Ka is equal to the concentration of H3O plus multiplied by the concentration of my anion divided by the concentration of my original acid solution. Now what I can do is I can plug in the values that I calculated in my Rice table, like so. And then I can experimentally solve for X. Now one thing that's really nice about this is that the X is going to be a very, very small number, especially compared to 0.15. So what we can actually do with that number at the bottom, that minus X, is we can actually cancel that value. That's going to make this a whole lot easier because otherwise we would have to use the quadratic formula in order to solve for X. So I'm just going to simplify. Multiply the two x's together to get x squared and divide by 0.15. And now I can solve for x relatively easily. And what I get for x is 1.64 times 10 to the negative third. Again, if you look at it, a very, very small number when compared to 0.15, which is why we can eliminate x in the denominator of that second step. We can then understand that x is equal to my hydronium ion concentration and then determine the pH by taking the negative log of that to get a pH of 2.78. So this is a bit complicated to start off with for sure, but in time you'll find that this gets much, much easier as we go through and do our calculations. A couple other calculations that we can perform here include percent dissociation, and percent dissociation can be calculated from the following. The percent dissociation is equal to the hydronium ion concentration divided by the initial acid concentration times 100. So much like the last time, in order to determine the H3O plus concentration, I created a Rice table. I have my reaction, my initial. I know that I'm going to lose one of my reactants to form two of my products. I therefore then plug that in to my equilibrium expression, and then I can easily solve for my H3O plus concentration. Once I get my H3O plus concentration, I can then plug that into my percent dissociation because I know what I started with, which is 0.050, my molarity for acetic acid. I know that my hydronium ion, based on my Rice table, my calculation for X, is 9.49 times 10 to the negative fourth. So I put that on top. I put the initial acetic acid percent on the bottom. I divide and multiply by 100 and find that I get 1.9% dissociation. Very, very small percent dissociation. Essentially what that means is only 1.9% of the acid actually broke apart into hydronium ions and the conjugate base. So let's look at some practice problems here. The ionization constant for acetic acid is 1.8 times 10 to the negative fifth. That for hydrocyanic acid is 4 times 10 to the negative 10th. In 0.1 molar solutions of sodium acetate and sodium cyanide, it is true that, and you're given a list of options here. Well, I think really importantly, the first thing we need to do is write out our equations for this when we put these two salts in water. Now, remember that when you put salt in water, particularly sodium, because sodium, the solubility rules state that it always forms an aqueous solution, so we're going to break those apart into their ions. Those ions are then going to react with water to form acids, like so. So we have our two reactions here. We have our acetate ion that reacts with water to form acetic acid and OH minus. And then we have our cyanide ion that reacts with water to form HCN and OH minus. And again, these are weak acids, so we're in equilibrium here. So in order to determine what has greater concentration, OH, H, whatever, we need to look at our equations here. There's really no H plus in the solution, so we can kind of eliminate A, B, and C here. But let's just kind of dive through it in a little bit more detail here. We also have two Ka values. The Ka value for acetic acid is much greater than that of hydrocyanic acid. That means that acetic acid is going to readily dissociate more than hydrocyanic acid will. As the Ka of acetic acid is greater, more of it is going to dissociate, which favors the reactant side of the equation because acetic acids are in our product side. Thus, less OH minus is formed with the acetate ion than with the cyanide ion. So because the Ka value of HC2H3O2 is greater, we're going to have more of it break into its ions, thus shifting the reaction more to the left than hydrocyanic acid would. If the first reaction is shifted more to the left than the second one is, then we're going to have fewer OH minus ions in sodium acetate solution than we would in sodium cyanide solution. So therefore our best answer here is D. Again, it takes a little while to kind of understand and get the hang of how these problems work. But the more we look at these and the more we practice with them and the more we work to understand how these things work, it becomes much, much easier over time. What is the pH of a 1.0 times 10 to the negative second molar solution of HCN? For HCN, the Ka value is 4 times 10 to the negative 10th. It gives us 5 answer choices here. Now, one thing that's very easy to determine from these, especially your acid-base stuff, the first 3 answers cannot be correct because this is an acid. And we know that acids have a pH that is less than 7, so we know it cannot be A, B, or C. So essentially it's either D or E. So one thing we can do is set up kind of a quick Rice table, and even as you practice with this more and more, you start to see trends in how to put these together, taking the Ka value, putting it X squared on top, divided by the initial concentration of the molar solution. So you can set these up pretty quickly. And what you get there is X for your molarity, 2 times 10 to the negative 6. The negative log of that, 5.70. So the correct answer here is D. Again, just more practice with these. Practice with these concepts, working with the equations. Working with the equations is going to be very important with this. And then also being able to write out those Rice tables and determine concentrations of hydronium ions in solution is going to be very, very important. So hopefully from this video, you're able to determine the concentration of solutions from weak acids and bases. You can explain the relationship between pKa and A, calculate the percent ionization, and write out weak acid-base solutions. We'll talk more about buffers in a video a little bit later on. Hope you guys have a great day. Thanks for watching, and we will talk to you later. Bye-bye, guys.